Hello, I'm Atindra Chaturvedi. In the previous section, we looked at an introduction to vSphere 6. We looked at the various advanced features in vSphere 6, as well as got some familiarity with the command line. We are now going to move forward and look at administering advanced vSphere 6 networking. In this section, we are going to take a look at the vSphere distributed switch advanced features. We are going to focus on three specific features, and the reason for these specific features is because they are usually misunderstood in my experience. So we are going to look at configuring and managing the NetFlow system. That's part of the vSphere distributed switch version 6.0. We will also look at network IO control and IOC version 3. This is a terrific feature. I think you'll enjoy that video. We will also look at ESXi6 command line interface networking. As I promised you earlier, we're going to look at all aspects of vSphere 6 from the command line perspective as well, because you need to become familiar with the command line to do advanced activities. And then another feature of vSphere 6 advanced networking is custom TCP IP stacks, where you have the ability to define your own TCP IP stack and obviously have configurations which are independent. So that's also a separate video that we will be doing. So with this, we are going to move forward to the next video. The three features that we're going to look at in this video are NetFlow support, traffic filtering and marking, and the enhanced multicast support for IPv4 and v6, which is now available. So I have now created a very basic VDS, vSphere distributed switch. It's called VDS 210. I'm in the vSphere web client. And as you can see, when I click on this, one of the options that actually comes up is NetFlow, which I will now click on. Before we start configuring NetFlow, let's just take a look at what NetFlow is. So some years ago, there was a big requirement to actually monitor what was happening within networks that were growing extremely large. So there was an RFC that was sent out to Cisco, and it was an information RFC that basically defined a protocol and a mechanism, what are called flow records. Now let's just define what flow actually is. So the flow would be from a specific ingress interface. We look at basically the IP source, the IP port, source port, the IP destination, as well as the IP destination port, along with the actual protocol, and in some cases the some of the TCP flags that actually come along with that flow. And the idea was that this information would be initially captured by the device, and then at intervals of time, it would then be sent over to what is called a NetFlow collector. And then the NetFlow collector would aggregate all this information and then provide means of reporting on it, either using reports or graphical user interfaces. So this has evolved considerably. There's NetFlow version 5, NetFlow version 9. There's also a version 10, and there is the more standardized version, which is called IPFix. So let's not go too much about those details. You can always Google NetFlow and take a look at exactly what all those are. For our purposes, the virtual distributed switch or the vSphere distributed switch allows us to configure NetFlow. And we have to do it in actually three places. You have to configure it at the level of the VDS itself, which is where we are. And then we have to configure it at the level of the distributed port groups, and then at the level of the VDS DV uplinks, just to be sure that it has a clean path through. So let's click on NetFlow and click on Edit. Now we are going to look at each one of these. So the vSphere distributed switch actually collects the information, the flow information as I defined earlier, and then at certain points in time, it sends it over to the NetFlow collector. So it has to know what the collector IP address is. So this would be an IP4 or an IPv4 address. And in our case, let's use 192.168.0.99. I'm going to leave the collector port alone. You can actually define the collector port, but actually let's try 5000. We'll give it a domain ID. Domain 1, leave it at 0. Switch IP address. So how do you identify the records from where that flow actually came from? So you need a switch IP address. In this case, I'm going to put in the host address. 192 is a distributed switch distributed across many hosts, but I'm going to give it 192.168.0.100 to identify that. Now the next set of settings are what are called advanced settings, and they really are not that difficult to understand if you realize that what a NetFlow exporter does, like our vSphere distributed switch, is that it collects flow information, and at certain intervals of time it sends that information over to the NetFlow collector. Usually that is done so that unnecessary CPU cycles are not taken up by gathering far too much information, but of course you then have the possibility of gathering less information than is useful. So it's really important to be able to fine tune the actual settings for NetFlow. But usually for the what is called the active flow export timeout, and many reporting systems are based on the fact that it'll be 60 seconds or 1 minute. What the active flow export timeout actually means is that the flow information is sent to the collector IP address basically every 60 seconds. The idle flow export timeout basically means that once a flow stops and there's nothing happens for 15 seconds, then basically it times out and the information is actually sent over to the collector saying that the flow has stopped. The sampling rate here it is 0, but it's a little convoluted, but let's give it a try. What the sampling rate basically says is that I will do one sample, and then what I'll do is I will wait for the X number of samples to pass by before I sample again. So for example, if the sampling rate was 2, what that means is that I take a sample and then I let 2 time slices pass basically, or 2 packets to pass in that flow before I sample again. So something like a 1:4 means I sample once and then let 4 pass by and then I sample again. So of course you understand if you sample very infrequently you may not get as precise information as you want, but usually something of the order of 1:4 or 1:5 does the trick. Internal flows are basically internal flows within the vSphere distributed switch itself. So it's between virtual machines. Usually we don't want to do that. We want to enable the external flows as well. And then we basically click enter, and it'll refresh in a few seconds. In the meantime, let's right click on our VDS again and go to distributed port group and manage all the distributed port groups together, just to be sure that we have good configurations there. So what we are looking to do here is basically to control the NetFlow configuration, monitoring. We select the port groups. We select both the port groups that are available on this VDS. We click OK. We again have to shift click to select both. I click on next. NetFlow is disabled. I enable it and I click next and finish, and that takes care of that. The next step is to go to the DV uplinks. I edit settings, and we again look for, in this case it look for advanced, and we make sure the NetFlow is allowed, and we click on OK, and that takes care of it. So just to recap, NetFlow has evolved quite a bit. The VDS will send NetFlow samples, collections over to the NetFlow collector, which one defines. And if you Google NetFlow collectors, you'll see there are many available, including those that are virtual appliances. So there's a company called Plixer, Plixer. They have a product called Scrutinizer that I use in my lab, and it really works very well. They have, of course, commercial versions as well, but they also have free versions if you want to really understand NetFlow and then at the right point in time move to a commercial product. So that's the way NetFlow actually works. Having looked at NetFlow support in the vSphere distributed switch version 6, let's now look at traffic filtering and marking before we proceed to the multicast support. Before we jump into the vSphere web client and start configuring the vSphere distributed switch, let's take a look at exactly what class of service means and differentiated services code point DSCP actually means. So when we're talking about traffic that is traversing a distributed switch, you have to understand that the distributed switch is then connected to a physical switch, and then after the switch, you are then connected out into the world of routers. So you have layer 2, and then you have layer 3. Layer 2 usually being at the level of Ethernet, and then you have layer 3 transport that is basically IP transport. Okay, so if you have traffic that is coming from your servers, your virtual servers, going through the distributed switch, and you have, say, two kinds of applications in your server, or even if you have a distributed switch, two separate hosts, one running a very critical and business sensitive kind of a application, and the other one is your email, which actually is now business critical in many cases. But let's just imagine that the email is less important. Now, if you have a limited amount of bandwidth and it goes to the virtual switch, the actual traffic flow is essentially, if you have not done anything else, given the same priority. But if there's a lot of activity on your business critical system, then you need to make sure that it gets through first, it gets priority, right? Now it should get priority from within the distributed switch itself, and we'll be talking about network IO control soon. But once we get outside the switch, what happens in the physical network? First, it goes through basically the Ethernet layer, then it gets to a router, and then it's basically an IP packet that is sent across. So how do you make sure that those Ethernet frames and those IP packets coming from your business critical system or coming into your business critical system have the actual priority that they want? That they want and they actually require for a successful experience. So there are two techniques that are used. One is called class of service, COS, and the other one is called the differentiated services code point, DSCP. So in order to ensure what is called QoS, this is QoS here, quality of service, let's just take a look first at what class of service means, COS. So class of service is a 3-bit field which is called the priority code point. It's within an Ethernet frame header, and even when using VLAN tagged frames, it specifies a value of between 0 and 7, which can be used by QoS disciplines to differentiate traffic. So what all that basically means is that within the Ethernet header, there are 3 bits that are called the priority code point, and obviously 3 bits will allow you to have 8 values between 0 and 7, and you can assign these frames the values as from between 0 and 7 depending upon the requirements. Now it obviously means that the physical switch also has to understand what you mean, and let's take a look at that. So if the value in the Ethernet frame or the Ethernet header has basically the value of 1, okay, it means it's a background traffic. Then the next is best effort traffic, excellent effort, critical applications, video and voice, you want to give higher priority. And then of course you have the inter-network control, which is basically routing control, and the network control, which could also be an inter-network but is primarily within routers to actually manage them. So this is a management plane, control plane kind of activity, not the data plane activity, which is basically here. So this is where your data would actually traverse. So if you have these applications and it's a high priority application, then you would probably want to tag the frames that are going out from your application to, say, the PCP value of 3, and this then becomes a critical application. Now this is just a tagging. The meaning of it can be whatever you want, but therein lies the problem. One needs to be sure that the meaning you gave 3 is the meaning that the network device expects. If the network device thinks that 3 is not a critical application, it has the capability of sending it back basically to a value of 0, which means it is totally a background. Okay, so it's important to understand that while these values are there, we all need to follow the same convention. We all need to understand that 6 and 7 are for inter-network control and network control. Okay, we all need to understand that the priority of 0 is basically background, and that best effort, also known as BE, is 1. In fact, the class of service value of 3 is used by FCOE, which is a fiber channel over Ethernet, to be able to provide a lossless traffic. So we discussed the layer 2 and why class of service is important there, because you need to make sure that the proper traffic is being tagged properly, so that the proper priority and the queuing in the physical switches can actually be given to it. Now let's switch from layer 2 to layer 3. In layer 3, there are 6 significant bits of the diffserv field, which are called the DSCP, or the differentiated services code point. The last 2 bits are basically used as explicit congestion notification, and sophisticated routers actually use this. So if the field is on, or the bit is on saying I have congestion, then it's a signal for the router to actually take some measures, including working with its own buffers, or including sending a signal to upstream routers that that interface is getting congested, and to slow down the transmission. So basically what it is that you have 6. It's called a diffserv field. We use 6. Okay, there's basically a one full byte, but that's last 2 bits are used for the ECN bits. So let's look at diffserv, right? So 1, 2, 3, 4, 5, 6. This is the diffserv field, and this is the explicit congestion notification bits. Okay, so what do they mean? So in your pass byte, you have, say as an example, this field. Now here again, okay, you have definitions, and these are definitions from different RFCs. So for example, RFC 2597 defines what is called assured forwarding. PHB means per hop behavior. Per hop behavior. Remember, you're now out in the world of routers, and the behavior, and it's basically a hop to hop, router to router means of sending the IP packet, right? So at every hop, you have to make sure that the router that is sending it out and processing it make sure that the DSCP settings are appropriate, so that the receiving router understands the critical nature of the game. Now, of course, there is no guarantee, because we are on the internet. Some router out there could actually bring everything down to exactly the same, and in likelihood that often happens. But again, the idea is that there are some conventions and some standardization that has been actually done there. The assured forwarding per hop behavior guarantees a certain amount of bandwidth through to an AF class, and allows extra bandwidth if available. So in configuring the routers, there are different amounts of buffers and queues and drop methods for traffic that are actually configured. So as long as those routers understand what they are looking at, and there is some common convention there, then the higher quality or the higher criticality traffic can actually traverse according to its needs. So without going any further, let's look at there's something called AF11, AF11, which is again assured forwarding 11. It has a DSCP value. The 6 bits are 0, 0, 1, 0, 1, 0, which basically translate to a 10, right? That's 2 and 8. 2 plus 8 is 10. Okay. Now drop. So the bits DS2 and DS1 specify the drop probability. Okay. So these bits here, okay, specify the drop probability. The lower that number, the lower the possibility is of it being dropped. So you could have traffic basically in the assured forwarding 11, assured forwarding 21, 31, and 41, and there. But even within each one of them, if you have 11, 12, and 13, then AF11 has the lowest drop probability. So in many cases, what one does is within the same assured, you make sure it's assured forwarding, but then you assign it to a certain class. Like for example, in here, so that the most critical application has, in terms of statistical probability, the lowest possibility of traffic being dropped. There is one specific value which is called expedited forwarding. The expedited forwarding per hop behavior can be used to build low latency, low loss, low jitter, assured bandwidth, end-to-end service through diff-served domains. So basically, a service like this appears like a point-to-point connection or a virtual leased line. So the code point for that is these 6 bits, okay, and it's called EF, expedited forwarding per hop behavior, and its DSCP value is 46. So at a layer 3, we use differentiated services code points. At a layer 2, we use the class of service from a value of 0 to 8. Okay, and in our examples, because we are now going to move on to our vSphere distributed switch, we are basically going to use AF11, 12, and 13, understanding that AF11 has the lowest probability of drops, and AF13 has the highest probability of drops, and we'll use a value of 46 as well, because in there we have to key in 10, 12, or 14 in the configuration for the vSphere distributed switch trafficking and traffic filtering and marking. So we are now back in our familiar vSphere web client, but it was really important to understand the differentiated services code point for layer 3 markings so that the routing devices can act accordingly, and then the class of service markings for basically layer 2 so that the switches can understand the requirements for that kind of traffic. So now we are here in our familiar VDS 210. Let's look at port group 2. I right click on that, edit settings, and we see traffic filtering and marking right here. I'm going to click on that. Its status is now disabled. I am going to enable the status first, and now we have the ability to basically create a traffic rule. So I'm going to call it PACT network traffic rule. There are 3 actions possible: allow, drop, and tag. At this point in time, we are simply interested in tagging. We will take a brief look at allow as well. So you can actually use it as a firewall also to allow, if you allow and drop traffic. But let's just stay with the tagging right now. Now we understand what the COS tag is. Down, as we know, the value is a 3-bit field, so the value is from 0 to 7. We know that if a class of service 0 is basically your default value, and then if I update the DSCP flag tag for layer 3, that's also a 0. So for class of service, let's make this 4. So, and we will make this expedited forwarding EF, which you remember has a value of 46. I'm going to use this for ingress and egress. The options that we have are both ingress and egress from the switch, or only egress or only ingress to the switch. Now this is the important part. I can either define that traffic using IP or MACs or system traffic. Let's first look at system traffic, because I've given this an expedited forwarding value. Let's look at system traffic. These are pre-populated values, so I can either say is or is not. So let's look at what we're looking for. I think management traffic needs to be expedited forward, right? Because we need to make sure the various requirements of this, and it's not overwritten by virtual machine traffic or any such thing. So expedited forwarding 46 is probably appropriate for management if we are not running either video or voice over IP or something of that nature. If you're not doing that, then this would be a good place for it. Now again, I decided to do that, but in a real production environment, what you need to do is to make sure you speak to your networking team to ensure that both of you use the same convention for tagging. Cisco Systems has defined different combinations of this that are available in Cisco documentation, and it's more than likely your in a Cisco data center that your engineering team is actually using those suggestions from Cisco, but please just make sure of that. One example is that class of service 3 is usually reserved in Cisco UCS, the Unified Computing System, for fiber channel over Ethernet lossless traffic. So I will click OK, and I click on OK as well. So what have we done? We have a traffic rule 1 that we're going to tag on our layer 2 network, class of service 4, and DSCP 6, and some ingress and egress. And as we saw, it's only for the management traffic. Let's add another one. We can say packed VMs. So this is for our virtual machines. Now we can update the cost tag again. Probably use a value of maybe like 2 for expedited. It is expedited traffic, and what we can do here is maybe give a value of, if you recall, we can give a value of 10. It's right here, a value of 10 for assured forwarding 11, and we will click on plus there, and we will say virtual machine traffic is going to be tagged like this. We haven't specified anything else here in terms of source ports or anything. So okay, so we really should change this. So we now have 2 network traffic rules. One is for VMs and one is for management traffic. Management traffic gets a higher priority on layer 2, as well as expedited forwarding code point or per hop behavior based on the 46 DSCP. And actually this is a pretty nice priority as well for VM traffic, with a class of service of 2 and a DSCP of 10. And that's basically how this actually works. I click on OK, and that is that. I look at the uplinks, and in the uplinks also I see traffic filtering and marking, and it's the same technique of tagging, allowing or dropping. We can explore allow or drop. So we can say drop on ingress or egress if there is traffic from some kind of a source port, any, and if there is a specific IP like 192.168. Let's say 0.50 that you do not want traffic to flow, you can do that, or you can specify a no, there's no range possible in this one. There's a range possible in the other one. Okay, so you can actually use it as allowing or dropping traffic as well. You can also allow, again the same. We're going to go to IP qualification, and matches does not match the different ones here. If I look at the same thing in the distributed virtual port group, I look at traffic filtering and mounting, and I click on plus. Now when I look at adding it based on new IP qualifier, I just want to verify that I have, now there's no range in here. Is there a range in here? No, there's no range in there as well. Okay, so this is how you actually do traffic filtering and marking and configure it. As you can understand, it's a really critical thing to make sure you're completely synchronized with the traffic that's flowing into the physical network and the expectations of the physical network. Now, before I cancel out of this, there is one more point I need to make, especially in a data center which has Cisco networking devices as access switches, because that's the first switch that a server actually accesses. Access switches have something called a trust boundary, which means that whatever traffic is coming into their ingress ports, they need to know whether it is coming from ports that are trusted or that are untrusted. Now in Cisco Nexus 5500 switches, for example, the default is that those are trusted, which means that since they are trusted, any markings of class of service and or DSCP that is in those frames is allowed to stay as it is, which means that you could do the markings as we just did in the distributed switch. Now, either, and I've seen this happen, that assumption is not correct, either because the switches are from a different vendor, or perhaps the switch was not entirely cleaned out and to a base configuration before it was installed again. And if by chance it has now set to basically the port on which this distributed switch is connected to be an untrusted port, what happens within the Nexus OS that runs on the Nexus switches is that everything is marked down to basically a 0. So you may have put in expedited forwarding 46, and you may have put in a class of service of 4 for your management traffic, but because the switch believes the port is on an untrusted boundary or an untrusted port, it marks everything down to 0, which means you are there among the garbage traffic that might be flowing. Now, I've seen this happen many times. So please, when you work on DSCP and class of service, make sure that your networking engineers understand what you're doing and that they can respond appropriately. In many cases, they can actually write ACLs to classify the traffic, and then depending on if you have specified class of service 4, and in their network they actually use COS 2, for example, they have the ability to automatically change that class of service 4 that you have given it in the distributed switch to class of service 2, which meets the requirements of the rest of the data center network. So this is a very important topic. It's not been much addressed, which is why I've spent a significant amount of time on this. Please make sure that this works the way you believe it really should. So we've spent a considerable amount of time on traffic filtering and marking, and especially understanding DSCP code points, expedited forwarding, per hop behaviors, and so on, as well as the class of service. So we now understand what one needs to do on a layer 2 and a layer 3 network in terms of marking traffic. Let's now move to the really excellent support that the vSphere distributed switch has for multicast in version 6. So to understand the enhanced multicast support for IPv4 and IPv6, we are back at the vSphere web client. But just like we did for traffic filtering and marking, before we proceed to understand how to configure it, which is actually a very simple matter, let's understand why it needs to be done. Multicast traffic is very different from unicast traffic. The focus in unicast traffic is more towards the destination. What is the route to the destination? How do I get to that destination? Right? Where is my gateway? And so on. So everything is oriented towards the destination because your source and destination are both known. In multicast traffic, it isn't the case, because think of it. If you have a video server and it's sending out multicast traffic, basically, Netflix kind of movies. If you sign on with your laptop and you want to actually connect to a movie stream, then what you have to do is that you need to actually understand what the source is. Since you are the destination, because the traffic will be coming to you, you have to understand and you have to sign on to Netflix and basically subscribe to that video stream, right? So it kind of works the opposite way. So looking at an example of a virtual machine, there's a virtual machine behind a vSphere distributed switch, and it wants to act as a receiver of a multicast stream. Now remember, the IP address range for multicast is quite different. So you look at 224, starting with 224, .0, and I believe it's a /4 or a /6 address. You can look that up. So as long as whenever the system recognizes that there's a multicast receiver wanting to subscribe to a multicast stream, what happens is that that request floats up through the switches. So let's imagine we just have physical switches. We don't have distributed switches right now. What happens there is that there are protocols in place now which are called IGMP. This comes in version 1, 2, and 3. IGMP stands for Internet Group Management Protocol for IPv4, and Multi-Listener Discovery Protocol for IPv6, also known as MLD. So it's a certain protocol. It's a protocol that has its own format and is understood by most modern switches. And what happens is this: when the IGMP join, which means that you want to join a certain stream, multicast stream, that IP IGMP join, or the MLD join request essentially, is actually sent up to your nearest multicast router. So it percolates up to the switch, up to your nearest router. And what happens there is that if the switch doesn't understand the IGMP protocol, and many older switches don't, then it just passes it right through over to the router. And what happens is the router basically says, okay, coming out of this port, out of this switch, I have a request for multicast address 224.x, and what I'm going to do is to just mark it. So when the video stream begins, or if the video stream is already running, it just sends that video stream down that switch port. Now, connected to that switch could be many different devices. Now, if the switch doesn't understand what's going on, it basically broadcasts that information to all the ports, which means that you have a huge amount of traffic coming into those ports. And if you don't need that traffic, then it's just wasted effort on part of the NIC, and obviously you have a slowdown in terms of your responses. So even if there was only one port into which there was one virtual machine, that switch starts broadcasting everything. And that's what IGMP snooping and MLD snooping basically does. It understands IGMP join messages and IGMP leave messages, so that when you're done with it, if you want to sign off that multicast stream, you can sign off. So what happens is when a multicast receiver sends an IGMP join request, the modern data center switch recognizes it. And what it basically does is, at that point in time, is it stores information about, if it's IGMP version 3, it stores information about the port and the IP address on that port. And then when the multicast stream starts coming in, it does not do a broadcast and send it to each and every port. It basically sends it down to that one port, which presumably has that one IP address, because normally one doesn't hang off multiple devices onto ports anymore. Okay, but anyway, you can understand what happens now. Instead of the broadcast stream coming into every port and then being rejected by all ports except the port on which that virtual machine or that multicast receiver is, you have eliminated all that hugely useless traffic. And if you have a 24 port switch or a 48 port or a 96 port switch, basically, one out of 96 will be the one that will actually get that multicast stream. So it is filtered. And the other it happens the other way as well. When you want to leave, you can do an IGMP leave, essentially, which means you want to sign off, and the switch understands that. And the reason this is important is because if you are the last person or the last device or the last application that wants to listen to that same multicast stream on that switch, it basically tells the router not to send the stream in at all. Okay, so as long as there is one active receiver, then that happens. And the switch basically has something called an IGMP querier capability, and there is a special advanced setting that is available for it. So every 125 seconds, it sends a query out to all the listeners just to verify that they are still interested in that multicast traffic. And if it does not hear from the multicast listener, either because of bad programming on that multicast listener or for any other reason, then it basically takes it off that list of ports and IP addresses to which that multicast has to be sent. So it's very important, because many modern vSphere components, as well as VMware products like network virtualization products such as NSX, one mode is for using VXLAN, which is the extensible LAN, virtual extensible LAN, that is used in NSX. There are three ways of actually working with it, and one of them is to use multicasting. Now, multicasting has been traditionally not used in a data center, but really it's a very efficient way of managing devices, as long as the proper snooping is set up in the switches. And it's very trivial. In Cisco devices, basically you basically set IGMP snooping on. I mean, that's really all there is to it. And it is the same thing here as well. When I look at settings, in edit settings, click on advanced, and you have IGMP MLD snooping or basic. I think it's good to set up IGMP MLD snooping anyway. I see no reason why one should work with basic. vSAN also, I think it's really good for vSAN as well, because only those devices that are actually connected to vSAN and require the different streams of multicasting that is used in vSAN, you can be very specific about what you receive, and the switch will be very, very efficient in actually doing that. So I would recommend setting this option always to be on IGMP MLD snooping in a modern environment. Now, data center network engineers don't actually like this very much, but when you have a good discussion with them after watching this video, you can explain to them why you really want to set this up and make sure that within the data center network this is set appropriately, and it is completely compatible with what is happening in the virtual environment. Having understood how IGMP snooping actually works, let's just take a look at some settings, advanced system settings that we can actually manipulate. So I'm looking at that same host that we looked at earlier, and I go to the advanced system settings, and then I scroll down to the net.igmp. So you can see that there's a IGMP queries. There are 2 queries to send during, after vMotion and teaming failover. Okay, but this is the one that I was talking about. The net IGMP query interval is the interval in seconds where for multicast snooping, it basically sends a query out to through all its ports, asking to make sure that there are devices still out there listening on multicasting traffic, and it just updates its tables, and based on the updated table, when the reply is received from its query from the multicast listener, it can update its table, and then if somebody has left or somebody has joined, it can actually clean up its tables and send the data coming in on those multicast streams down to the proper ports and the proper IP addresses. So it happens by default every 125 seconds, but again, if you're into tuning mode, that's how it will be done. Your IGMP router IP, you don't really have to set because your network is set up. You basically a gateway out of your switching environment into a router. I mean, that would be essentially the last router in that chain, or depending on which you're looking at it, first or last router in that chain. And that has to be configured with multicasting. Protocol independent multicasting, PIM, is usually the way that's done. PIM sparse mode and PIM dense mode are the 2 terms that are used. You can Google that. It's actually pretty straightforward. And I would encourage you to go through a primer on multicasting. It's going to be really coming in handy as we move forward with more and more products in the data center that use multicasting. So with that, we have covered a lot of ground. Very advanced capabilities, but the ones that cause a lot of problems in my experience in modern data centers. So setting up appropriate NetFlow support, and especially the 2 timeouts, to make sure that it's usually set to 60 seconds or 1 minute, because most reporting systems almost assume that sometimes. Traffic filtering and marking, we looked at extensively as well with class of service as well as DSCP, and you understand why this would also cause problems in modern data centers if it's not done consistently. And of course, the enhanced multicast support has become very important because many modern products use multicasting in the way that it's supposed to be. Multicasting is not just for streaming video. It is used for making sure that there is the least amount of traffic and the maximum efficiency within your network. So it's very easy to set up. There's nothing complicated. I actually think that multicasting is easier to understand than unicasting and broadcasting, which we are all used to. You just have to learn to turn this thing on its head and think of it not from the viewpoint of getting to a destination, but from the viewpoint of actually subscribing to a source. Once you get that idea, then multicasting is actually very easy to understand. Let's see what we have next in store for us. The next video will be about Network I/O Control version 3, a very, very sophisticated and elegant way of managing the amount of traffic and the bandwidth and stuff like that is allocated to different streams that are traversing your vSphere distributed switch. I look forward to seeing you on the next video.